I like chapter 3. It's fun.
But is it fun for you?
It might be fun for you. It might not. I find it interesting. There are a lot of real-world problems, and it's a fairly algorithmic chapter, meaning do this, do this, do this. Oh, look, you have the answer. And you'll see today, we're going to start the first half of the lesson is fairly theoretical. The second half is all just grinding numbers out, and it's very straightforward. We are going to talk about Extrema on an interval. I'm going to start, well, first I have to do the objectives. Let me get that out of the way. Okay, so you should be able to, definition of Extrema, we'll talk about that on an interval. And then we're going to talk about that same thing, but on an open interval versus on a closed interval. And then most importantly, I was shocked, by the way, fourth period, how many people could not do the following. Can any of you not snap your fingers? There was at least 6 people in fourth period that could not snap their fingers.
I used to think you had to go like this.
Okay, so I'm gonna count down 1, 2, 3. I'm not gonna say it though, but when I get to 3, everybody snap their fingers. Okay, ready? Nice. All right, we'll see how that sounds later. That was fun. Okay, Extrema. I'm gonna start with the fancy calculus speak, and then transition from there into the English. Because I think it's important that you understand what this mess says. Okay? So I start with a function, f, on the interval I. And so that interval can be anything from 0 to 5, from -4 to +4, wherever the interval covers. And I have some number c that's in that interval. So if we go from -4 to 4, maybe we pick the point 2. Then the two numbered things are your definitions of what a minimum and a maximum is. A minimum would be the point where all the other points are bigger. The maximum would be the point where all the other points are smaller. Okay. And then we get into a whole bunch of verbiage here. They give you a little language lesson that if you have extrema is a plural, the singular is extremum. We're going to talk about minimum versus maxima. We're going to talk about minimum versus minima, which sounds like liquid hot magma. Do you guys even know who Austin Powers is? Yeah. Okay, just checking. I don't know where we're at there. And we're going to also talk about the difference between absolute max and mins versus relative max and mins. They come up later. In English, the biggest point is the maximum. The smallest point is the minimum. Pretty clever. So we're going to start by taking a look at a couple pictures and make sure that you understand what the minimum, minima, and maxima are. And then once we have that, then we'll start doing some calculations. You are, by the way, going to need your calculator, so if you don't have it out, please get it out so that you're ready when we get into these fun calculations. Gracias. Are you done with this slide? We're good? Okay. So let's start with the picture on the left. I took a chunk of a parabola and I put it on an interval. So I went from -1 to 2. And I included the endpoint. So notice that's a closed interval. Brackets instead of parentheses. It's silly to ask because it's labeled in the picture, but if you look at the picture, that's the minimum. Why is that the minimum? Because it's the lowest point on the graph. Why is this the maximum? Because it's the highest point on the graph. What about that point?
That's a point.
Just a point. As is that point and that point and that point and all those other infinite number of points. So the maximum and minimum are just purely that. The highest point and the lowest point. Are you good on that side? Yes? Okay, now let's look at this. The way I changed this one is I put it in parentheses. I did not include the endpoints. Are we all in agreement that that's still the minimum? Still the lowest point on the graph. Do you see why, or can somebody explain to me why that is no longer a maximum? Becky?
That point doesn't exist.
Okay, so
It's an open interval, so you can't have like a point to add.
why can't I do the point right before it?
Because
I'm sorry?
You get infinitely close.
But I can't get to that point right before it? Isn't there a point right before it?
Yeah, but it's not the maximum of the function, or it's not the end of the function.
But if I don't,
It's,
if I'm looking for the person in the front row farthest to the right, but I can't include Olivia, why can't I just come here?
Because there is still theoretically a point there.
So you're saying there's more people jammed in between them?
They're invisible.
No, I'm just saying like Olivia, even though if you can't include Olivia, Olivia's still there.
So why can't she be the person furthest to the right?
I don't know. She could.
Because she's not included. Okay.
Yeah.
Do we understand what's going on? Maybe I'm trying to explain it too much and you understand. Do you understand why this doesn't have a maximum? I want to get up to that point, but I can't get to that point. And so my statement about we'll take the point right before it makes no sense because how many points are right before it? Infinite. So I get really close. Okay, so if this is at, where is that point? 2, 5. So I get up to 4.9. Okay, well I'm the point right before it. Oh no, wait, I can go 4.95. I can do 4.99. I can do 4.999. So I can always get closer and closer and closer. Therefore, it doesn't have a maximum. That is possible that functions don't have maxima or minima. A lot of it depends on whether you include the endpoints or not include the endpoints. Okay.
It'd be like the limit. Oh, I guess it's just a little bit not.
Correct, but we don't normally combine limits and maxima or extrema. But yes, you're right, it would be the limit as you get very close to that.
Just because they didn't feel like it?
They just avoid it.
No.
Yeah. Okay, so here's a different graph. And let's suppose what I didn't do, hold on. I didn't, whoa, there's a mess. I didn't put endpoints on here. So let's put this endpoint on there, and let's put that endpoint on there. And if I just look at that graph, are we all in agreement that that is the max? Because it's the highest point on the graph and that this would be the min. Are we good to go there? Okay, those are called absolute or global max and mins, meaning over the entire graph, that's the highest point, and over the entire graph, this is the lowest point. But now we can look at smaller chunks of the graph, and so you'll see here, I've got this little part of the graph put in a box there. I'm just looking at a smaller point of the graph. In that, I don't want to use the word point, a smaller section of the graph. In that smaller section of the graph, I still have a highest value, which they label as a hill, that point right there. That's called a relative max. It's a max in that small little neighborhood. We talked about neighborhoods a long time ago. But it's not the highest point over the entire graph. Okay, so this is an absolute max. This is an absolute min. This is a relative max. And then, of course, this would be a relative min. So it's the smallest value in a small portion of the graph. Now, how small of a portion of the graph are we going to talk about? Nothing ridiculous. We're not going to be talking about infinitely small chunks of the graph. We're just going to be looking in smaller neighborhoods, not the entire graph. Does that make sense? Okay. Graphs can have only one absolute max and only one absolute min. They can have a ton of relative max and relative mins, depending on the function. Okay so far? I talked about that already. We'll skip that. Okay, now we're going to do some exploration here. I have two functions for you. One is 9 times the quantity x squared minus 3 over x cubed, and the other one is sine x. I would recommend going backwards. Do b first, then solve a. What I'd like you to do is take the derivative of each of those functions and plug in the x value of the maximum. So notice the sine has a maximum here at pi over 2. Take the derivative, plug in pi over 2. Come over here, take the derivative, plug in 3 into that function. So you don't need to simplify it, just take the derivative, plug in 3. Don't be bashful about using your calculators. Do that now, please. It'll be good practice too. Take the derivative, put in the value, the x value of the maximum. Question? I didn't ask you for an answer. I said if you had a question. It was technically a question. And the reason I said do B first is because it's considerably easier.
Of the maximum, did you say?
Yeah, put in the x value of the maximum. So in A, put in 3, and in B, put in pi over 2. Let's do it yourself. You know what I'm saying? Uphill both ways, bare feet.
Yeah. So if you have any corners specifically or money to
Okay.
donate,
Alright, I'll let you know.
okay, that'd be awesome.
Alright, let's do B first. Derivative of sine is cosine. Cosine of pi over 2, 0. Good. Anybody get the derivative for A?
I'm not done.
Just as a quick survey, no right or wrong answer. How many are doing a quotient rule for A? And I assume the rest of you are doing a product rule? Okay. Either one in this case doesn't matter because when you're done, you're just going to plug in 3. Having done them both ways, I think this one's actually easier to do as a quotient rule. You got it.
I just moved on now.
Is the answer supposed to be up there?
It's not.
Probably a lot easier.
Oh, it is, isn't it?
Yeah,
Look at that.
thanks.
Well, I just said that,
Whoops.
the 9.
Yeah, we're just kind of just chilling.
So, John is fairly observant. I obviously am not. The answer to A is up there.
Where?
F prime of 3 is
Oh.
0. Okay, so now, Allie,
Yeah.
why are both of the answers 0?
Well, there must be something that makes it 0 every time. When it's the maximum, when you take the derivative of the function and then put in the maximum, it'll
Correct.
always be 0.
Do you know what that thing is?
No.
Gabby? Beautiful. It is a horizontal tangent line. So we start to fit puzzle pieces together. For instance, you've been doing this calculation for weeks now. Take the derivative, set it equal to 0. Well, why do I care why I'm setting? Why do I always want to find the horizontal tangent line? Why horizontal? Why not something else? Well, now you start to see why we want the horizontal tangent line. At all these maxima and minima, the tangent lines would be horizontal. And again, we start to fit these things together, and you see how this works. For those of you that may have struggled with part A, I do have the derivative here. I did a quotient rule, then simplified it, which I didn't even need to do because I could just plug 3 into it. And you see the top gives me 0, and the bottom gives me 3 to the 4th, which is 248. No? Yeah? 3 to the 4th? 81, 240, 240. 243?
3 to 4?
3 to the 4th.
I thought it was
81.
Oh, I threw an extra. I did 3 to the 5th.
Yeah.
Yeah. What's 81 times 3? 243?
Yeah, it's 240.
All right, just checking. That's overachiever.
I got 0.
Sorry, 81. And so we have 0 over 81, which is just 0. Okay? And again, why does that come about? Because if it's a max or a min, it's going to have a horizontal tangent line, and that's why we want to set these derivatives equal to 0. We're going to be doing that simple practice a lot. Take the derivative, set it equal to 0, solve. We did this one already. Okay, we get 0. Great. Okay, let's move on. Now, when we find those values, in other words, those values being the derivative, the values that make the derivative equal to 0, those are called critical numbers. Okay. X values and the special points are called critical numbers. However, one thing I neglected to mention is not only do we get critical numbers where the derivative equals 0, we also get critical numbers where the derivative is undefined. So if I go back to the previous example, this one, I get a critical number here because it makes it equal to 0 when x equals 3. What would be the other critical number? No? Oh, -3 would also work. Yes, thank you. And?
0.
0, correct. So the 3 and -3 work in the top to make it equal to 0. 0 makes the derivative undefined. So those, all three of those are critical numbers. And we're going to practice that in a second. Two scenarios. Horizontal tangent line, we did that already. Or where the derivative does not exist. That's called a cusp or a corner. Those are going to be things where it gets weird. So we're going to want to find those points. Okay, we're almost done with the theoretical stuff here. We'll get into the calculations in a second. There's the formal definition of a critical number. All that says is that it's where the derivative is equal to 0 or it is not differentiable. The second one is important. So we've talked about, maybe we haven't talked about, we talked about golden retrievers and dogs.
Only we should track them.
All golden retrievers are dogs, but not all dogs are golden retrievers.
Yeah.
Okay, so we understand the relationship there. The same is true with extrema. All extrema come from critical numbers, but not all critical numbers give you extrema. Should I say that again? All extrema come from critical numbers, but not all critical numbers are extrema. Sorry about the dog. You okay? Okay, good. The places this is going to be most important is if you start looking at functions and cranking out the critical numbers, you might get 3 or 4 critical numbers, but maybe only one of them represents a maximum or a minimum. And so just because you get 4 critical numbers doesn't mean you have 4 extrema. Question?
So it's only a critical number if the derivative is 0.
Or undefined, right? Because you got 2 parts to it. All right, question?
For what you said about like how not all critical numbers are extreme, then is that if there are multiple maximums and minimums in like an interval, and you want to find the maximum, or is it just?
You'll see in a second. My next example will actually answer your question. Okay, so now we got to find it. So now we're done with the theory. Before I move on, do you understand the idea of maximum and minimum? Okay, good. Absolute versus relative. We're going to spend most of the time looking at relative. However, my first example is actually one that focuses on absolute. So this is the process we're going to go through. Like I said, we're going to do this a lot. This is for finding absolute max and mins. Take the derivative, set it equal to 0. That will take care of step 1. That's how you find the critical numbers. Step 2, figure out what the y value of each of those critical numbers are by plugging it back into the original function. Step 3, check the endpoints. In other words, find the y values of the endpoints. Step 4, just look at the values. The biggest one is the max, the smallest one is the min. Done. Pregunta?
What about when? Can you set it equal to undefined or?
No, but you will see when you take the derivative, the critical numbers will be generated from not only where it's equal to 0, but where it's undefined. Especially when you're dealing with rational functions. You're going to want to set the numerator equal to 0 to to get the values where it's equal to 0. You set the denominator equal to 0 to get the undefined value. Okay? I know you're still right. On the first example, we're going to cheat. We're going to cheat by looking at the graph first, and then we'll see what we can tell from the graph, and then we'll crank out the numbers to make sure it matches our answers. You with me? This isn't a normal procedure. Like I said, we're cheating a little bit. Okay, for those of you that are done writing, open up or turn on your calculator, open up y equals, and put the following function into y equals. I'll come back to this in a second. Put that function into y equals, please. 3x to the 4th minus 4x cubed. Then set your window to -5 to 5 for both the x's and the y's, so you can get a good picture of what's going on there. Does somebody need me to go back to the last slide?
No.
Yes? Okay. There you go.
Do you want the window to be?
Wait, what was the function?
3x to the 4th minus 4x cubed.
And -5.
-5 to 5. Good? Okay. So look at the picture. What can you tell me about the picture?
Looks like a
Does it have an absolute max? Now hold on a second. I forgot to mention this if you didn't see it up here. We're putting it on an interval. So we only care about that graph from -1 to 2. So I'll ask my question again. Does it have an absolute max? Yes. Does it have an absolute min? Yes. Does it have any relative max and mins? Yeah. Are there any, well, I asked, any relative max, any relative mins? Okay, so the graph has that little bump in it, but it's basically a parabola with like a growth on it. You with me?
Yeah.
Okay, good. So now let's talk about the numbers. First things first, I want to find the critical numbers. So I did the derivative for you, because it's ridiculously easy, but set that equal to 0 and find me the critical numbers, please. While you're working, I'm going to ask a question. Are there any points on that derivative that are undefined?
Wait, how do you find the critical numbers?
I'm sorry?
How do you find the critical numbers?
Set the derivative equal to 0. Are there any points on that derivative that are undefined?
No.
No. It's a polynomial. It's good to go. Hold on. GCF, kids. Where are the critical numbers? Danny?
0 and 1.
0 and 1. Beautiful. We good?
Yeah.
Factor out a common factor of 12x squared. Use the zero product rule. Where's 12x squared equal to 0? At 0. Where's x minus 1 equal to 0? At 1. So we have two critical numbers there. Okay? Which means at 0, it might be a maximum or it might be a minimum. At 1, it might be a maximum, it might be a minimum, or it might not be anything. How do we check? Well, we then have to plug in some numbers. Since you have your function already in y equals, we can use the calculator to cheat, go to the table, and figure out the 4 values that we need. So what are the 4 values that we now need?
-1, 0, and 2.
-1, 0, 1, and 2. Which you should be able to read off the table. Normally you would have to plug them back into the original function and calculate it, but it's done it for you already. And we get that. -1 is 7, 0 is 0, 1 is -1, and 2 is 16. Then there's no trick to this, it's just this is all you do. Which one of those numbers is the biggest? 16, that's got to be the maximum. Which of those numbers is the smallest? -1. It has to be the minimum. And remember, we're looking at y values. How high up and down does the graph go? Question?
And you put it into the
Correct. Excuse me, into the original function always, because we want to know how far, how high up or down the original function goes. Question?
Yeah, my table did not have those. It had a bunch of decimals, so does it work if you just plug it in?
The problem along extra.
There you go, Lassie. That's all great now. Okay, we good? That's, now by the way, this is the absolute max. This is the absolute min. Notice I have a critical number here. That critical number did not give me a max nor a min. That is possible. However, my maxes and my mins have to be critical numbers. Okay? Good? Yeah.
So did you plug in the x equals 0 and x equals 1?
Yeah. But then I also plugged in the endpoints because our interval goes from -1 to 2. Question?
Would you always just plug in the endpoints?
When you're looking for absolutes, yes. Okay, any other questions? All right, this will be fun. Blah, 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 did that already. Yeah, we talked about that. Okay, find the critical numbers. I'm going to talk while you're working. One of the things that we worked on was factoring derivatives to turn a sum into a product. This is where it becomes relevant. You'll see when we solve this problem at the end, we don't want it to be so-and-so plus blah, blah, blah. We want it to all be multiplication because I need to be able to figure out where is it equal to 0. Don't worry about negative exponents. Leave them. You'll see why. Factor. Once you get the derivative done, you got to clean it up. Factor that, because again, we want to turn a sum into a product.
So it's like multiply everything out?
No, oh gosh, no. No, factor out common factors. Anybody making any headway? All right, let's make sure we all have the derivative together. 2 times x plus 7 times x minus 8 raised to the 1/3 power. I'm sorry?
You did x minus 3.
Correct. I was just seeing who's paying attention. Thank you, Abby. Good. I'll give you a point for that one. Is it EY or Y?
Why?
It's a reasonable question. Some
No,
people.
someone said EYI and it made me laugh.
EYI. We're a little hard over the I.
That's probably the name street. My cousin's name is Chloe. She's supposed to be
Abby.
Abby.
Abby, time for dinner. What are we eating, Paul? Okay, we good on the derivative?
Oh, yeah.
Notice there would be chain rules, but the chains in this case are 1, so they don't matter. That's a sum. Sum bad. Wait, question?
I was going to ask,
Go ahead.
would you factor out an x plus 7 and an x minus 8 to the negative?
That's exactly what I would do.
Where did the negative 2/3?
Minus 1.
1/3 minus 1.
I see it there.
Going to take out an x plus 7. Which x plus 7 do I take? X plus 7 to the first or x plus 7 to the second? The first. Outstanding. We're going to take out an x minus 8. Which x minus 8 do I take out? The 1/3 or the negative 2/3? Negative 2/3. Okay, now you got to be careful. Big bracket. When I take an x plus 7 out of the first term, I'm left with nothing. Just got a 2 sitting there. When I take an x minus 8 to the negative 2/3 out of the x minus 8 to the 1/3, I'm left with just an x minus 8. That's why we take out the smaller one, because most of the time it will reduce to 1. Plus, I got rid of one of those, so I'm left with an x plus 7. I got rid of this whole thing, but I left a 1/3 behind. This makes me happy. Why does it make me happy? Because I've turned a sum into a series of products. So if I'm looking for a critical number, this puppy has to be equal to 0, which generates 3 equations. What are those 3 equations?
That's a good question.
Hence the reason I asked it.
X plus 7 equals 0, x minus 8 to the negative 2/3 equals 0, and everything in total.
X plus 7 equals 0. X minus 8 to the negative 2/3 equals 0. And this business, which is 2x minus 16 plus 1/3 x plus 7/3, has to equal 0. Let's start with the easy one. X equals, so proud of you guys.
Thanks.
X equals negative 7. How about this guy?
Oh, 8.
Okay, so let's be careful here. Does 8 make this equation equal to 0? No, it makes it undefined, but we still want to count it.
Oh.
Whoops, equals 0. That's horrible.
So we have to get 8.
Oh, yeah.
Looks like a 0 with a haircut. There we go. Okay, does everybody understand why that's undefined? Negative exponent would move it to the bottom, but it still counts as a critical number because critical numbers are determined where it equals 0 or where the derivative is undefined. Okay, how about this puppy? Yep.
Yep.
Yep. 7/3 x minus 41/3 equals 0. And yes, you have to be able to work with fractions. Move that over, flip it over, and so x equals 41/7. I'm pretty sure. I'm going with it.
Yeah.
No?
41.
Yeah. All right. 3 critical numbers. We have, at this point, we don't care if those are maxima or minima. We'll do that later. We just want to be able to find the critical numbers. So I've got 3 critical numbers. Tomorrow we'll learn what we're going to do with those, now that we found them. Okay? Any problems? That's about as bad as it gets. Adam?
You do the, like, the
Yeah. I moved forward. You're talking about this?
no, the middle one.
Yeah.
So get-
If you want, if it helps clarify it, we could rewrite it as 1 over x minus 8 to the 2/3. That can never equal 0, but it can be undefined. So 8 makes it undefined, so we include it as a critical number. Okay? Any other questions before I erase? Beautiful. Dun, dun, dun. Oh, look, we got all the right answers. Woohoo!
Happy car. Family car.
I'm very proud of this, by the way.
Big family car.
Or if it's an
Chrysler.
Altima, so maximum. That's a Nissan Altima.
It's the Nissan Maxima.
Oh.
Oh.
What are these? What?
The minimas.
No. What is this?
A family.
And they are?
Minimas.
Relative.
They're relatives. Relatives. Is that a pity clap or
Family goes.
How long did that
what
take?
percent? Like 10% pity clap or 90%?
Like a 75.
75% pity clap? Wow. John, go get the dog, will you? Okay. Yes, John.
How long did that take you?
To find the pictures or to come up with it?
Both. Oh,
30.
like, the pictures probably took you like 5 seconds total.
Yeah, and the joke took about the same. I, yeah, so, you know, go.
So like 10 seconds.
10 seconds of commitment was about all. So that's why I'm not extremely upset about the 75%.
That's great.